Hello, everyone, and welcome to a deep dive into technical careers with me, Anirudhan, Badrinath, and the speaker today, Vasu Vijay. So before we start, let me quickly introduce myself. I am one of the founding members and a student leader at DYC since 2018 when it was founded. I'm currently a second-year student, computer science student at UC Berkeley, and my area of specialization is in data-driven algorithms, specifically in machine learning, natural language processing, and algorithms in general. This nonprofit organization, DYC Design Your Careers, is essentially a platform that helps students showcase everyone's skills and their talents by running all sorts of activities, programs, workshops, and fundraisers. And essentially, it's tailored by and for students to really harness and showcase their skills and talents. And for more information, feel free to visit the website listed here or check out the video that's linked as well. Now, this series is a very special series because we get to talk to some of the leading experts in different fields, in different industries. And essentially, this is the idea behind this is we're trying to provide opportunities for perhaps people in high school or college to gain work readiness and exposure with what these industry experts may have to say with regards to how they got started and how they experienced the industry. And this may come through any sort of field: technology, music, sports, science, robotics, arts, dance, or what we'll talk about today, which is a technical career. All right. So our speaker today is Vasu Vijay. He's a VP and a general manager at eProbito. He's a CTO at Capstone Capital, and he's a product evaluator at Microfocus. And all in all, he has over 35 years of industrial experience since 1984, when he was a project engineer at Siemens. Welcome to the show, Vasu.
Thank you. I'm honored to be participating in this exercise. I think it will prove to be very valuable to the students and others who want to know and understand a little bit more about the variety of topics that you're going to cover.
Sounds great. We'll start with the questions because those provide, I think, a great introduction to who you are as a person and how you got started. All right. So the first question is sort of explain how you got into the technical field. What's really your story of how you got into a 35-year-long technical career?
Very, very simply put, I'll keep it short. I had no intention originally of becoming an engineer or a technical person. I would have followed my dad's footsteps and gone into banking. It was happenstance that I got into engineering, and what I discovered around the fourth semester, if you will, in the second year of my journey in engineering, was that I was good at it. And when you're good at something, then you really want to do more about it. You develop a passion around it simply because you're good at it. But the real turning point as to the value of getting into a technical career came when I was working at Siemens, and what I had to do was, and you can imagine a fresh graduate from an engineering school, long time ago, having to design something called a twin boom stacker. It was a huge piece of equipment, and I had to design the control system for that. And it was something new. It had to use electrical components for memory. We're talking of the days when computers and inbuilt systems and all that were just starting to emerge. There was no concept of IoT. And you had those old Siemens and Allen Bradley programmable logic controller systems that were just entering the market in any great shape. So those days, and when I worked on the design there, it said to me that you're creating something that is actually going into the field. It's going to be working at a steel plant. And the beauty of it was I was able to go to the steel plant and see it working 1.5 years later, which was, I think, the starting point for me to get into something on the technical side and the engineering side, the design, the build, the testing, and then you see it actually working in the field. And I did take a slight detour. I took a detour by getting myself a master's in business administration, which helped me understand how technology really fit in with the business, no matter which way you look at it, not just the engineering side, but also the business side, the administrative side, the finance, the supply chain, and so on and so forth.
Sounds good. All right. Since we've talked about sort of what pathway you took to becoming and coming into the technical career, what other kinds of pathways do you foresee to enter a technical career? And are there any that you think are particularly noteworthy, at least in this time and age? For example, like the traditional pathway is obtain a bachelor's degree, get a lot of work experience doing internships and all those kinds of things, and then join for example, software engineering or engineering position. And that's typically what students who want to go into technical fields are encouraged to do. Do you think there are any other pathways that are very interesting, and what do you see happening in the future in that regard?
So the traditional path will still continue. And I think for most of the people, the traditional path is a good path. It's a well-worn path. It's a path that people know. It's a very traditional, go get a degree and then jump into the field, get experience, and then move on from there. But it is the non-traditional path, I think, that will kind of take you elsewhere and potentially expand your own knowledge and skills tremendously so that in the shortest run, you can become much, much more experienced and valuable and productive. What do I mean by that? I mean, I'll give you examples, anecdotal examples, but I'll also give you something that's could be very interesting. Just imagine that you did go through the traditional path of getting internships and then joining a software company and so on and so forth to be on the technical side. Right now, the technical side seems to be mainly software, or if hardware, it's chip design. But there are lots of other technical jobs which are not necessarily related to computers at all, right? So when you say technical and technological jobs, those are not purely related to computers per se. Computers are pervasive. They are all over. They are the life and blood of practically every organization, product design, product, and so on and so forth. But they are not the be all and end all. You still need the mechanical engineers. You still need the electrical engineers, if you will. You will still need the other folks who did do the other stuff. So in many of those kind of areas, what might be interesting, at least in the first few years, is to try to gain breadth instead of depth. What I mean by that is that if you jump in and you jump into, let's just take computer science. Let's just take yourself for a minute. Since you said you're interested in algorithms, machine learning, NLP, and if you decide that that's what you want to do for the next 30, 40, 50 years of your life, and you jump in, and that's fine. You could change careers in the middle, but that's what you're going to do for the initial large chunk of your time. Whereas if you had exposure to a variety of things, even in the computer science field, you might find that there are other things also just as attractive. More, you have been given an opportunity in this space to learn this, but there are other things too. And as we know, no one can be a generalist. You have to be a specialist. You cannot learn all of technology. You can learn something and become really, really good at it. But what is very important is when you make the decision that you're going to spend a lot of your time, energy, and your life working around something, you have to identify that with some greater measure of certainty, in the sense that it should be something that you like to do, even when you're not at work. It should be something that should give you joy at any given point in time. 5 years after you're married, you have kids, it still should give you the joy. You can't keep changing your vocation every time because something did not seem nice or did not work out. So the most important thing is you at least initially, gain a little breadth. And for that, to gain a little breadth, I would say some kind of a career path which takes you into either working for a small company, very small company, a startup, some kind of things that exposes you to the entrepreneurial spirit, that exposes you to the fact that when you're working for a small company, you take out the garbage. There's not many other people who will do that. There'll be four people in the company who are trying to build something for a vision, and you will take out the garbage. You'll sweep the floor. You will make coffee for everybody, even though you might say, I'm this kind of guy. I'm your position, your title might be really fantastic. Even though there are four people in the company, you might be called the CEO, you might be called the VP of this or that, but you'll still have to do everything, and that gives you a certain breadth. The other thing that'll give you potentially breadth is, and here's, you got to be very careful if you join or jump into the right consulting firm, which will expose you to a variety of projects with potentially different technology, different aspects, and different things, skills that you have to learn. The third thing would be when you talk of the path to success and so on, is the world has changed. As I said, for 80% of the folk, getting a degree and then jumping into consulting or some kind of entrepreneurial venture is a good idea. For the smaller percentage of folk, whether it's 5% or 20%, the paths are different. You could, after high school, you could, if you're good at something, get a job in even the software industry. And you could get a job in an R&D organization. I'll just give you a couple of anecdotes. And you don't have to be necessarily extraordinarily brilliant for this. Right place, right time occurs when you are there and you're available at that point in time. The opportunity never knocks. I don't think it knocks twice. They say opportunity never knocks twice, but I don't think opportunity ever knocks. You just have to grab it as you go. And the example that I'd give is I know a high school student who didn't even complete high school, and he got a job offer simply because he knew a particular piece of technology really well, got a job offer. It was, in fact, close to what I earned right now at that point in time. But that's not the point. It's not the money part of it. It's the fact that you are that at that juncture, can you take the leap? Do you have the risk tolerance for that? Do your parents have the risk tolerance for that? And so on. That is very important. But those are all the unconventional ways of getting in and carving a path for yourself. The other example that I'd give is I have spoken to and I've been in touch with a lot of folks at the various R&D organizations in various parts of technology, right? Not just computers and computer science. But in most of these places, I've noticed that they have slots, or they welcome input, and they welcome the hiring of fresh talent, which does not necessarily have the so-called academic degrees. I have walked into R&D organizations where a high school graduate is leading a research team, and you'd say, what? And he doesn't have a PhD. He's not from one of the Ivy League schools. He's not, but he's there because over time he has shown that he is capable of doing things, and he's capable of doing things because he has learned it, not because he got a degree, which in general is a ticket, it's a door opener, but because he has done that. No, I'm not advocating anybody to drop out of school. What I'm suggesting is that just because you don't necessarily get the school of your choice or get the major of your choice, or just because you are doing something else, you've got other constraints, financial, other constraints. Don't let that stop you from getting into a technical career, because you can make it. It is not quote unquote rare. It is in fact much more obvious when you kind of look at the pathway, and if you look at various statistics. In fact, the best computer programmers are not the engineers, but the guys who come from the arts and the English background. You've heard that before, and you've seen that too. And the reason for that is the old saying is, computer science really science, or is it an art? And a lot of people believe that the art, the coding and stuff like that that one does in programming is maybe science, because you can put a hierarchy through it, put procedure through it. But the actual innovativeness or the innovations that come through are because of the people who think like artists, who think creatively. And 9 times out of 10, to in order to conform to what engineering teaches you and the procedures and the paths and so on and so forth, you tend to lose a little bit of that creativity. It comes back again after a while once you get into industry and you start asking a lot more questions. But the point I'm trying to make is that the traditional pathways are important, education is important, but don't let that be a damper or, uh, if you will, a road bump towards your goal. You can do whatever you want, no matter what has been in your constraints have set for you. That's all.
Yeah, I completely agree that implementation is, of course, a science, but I think innovation is not a science at all. I think it's much more of an art, like you said. Uh, One question that I have is, we've talked a lot about obtaining and going through the pathway to getting a technical career, but I think as difficult and as challenging as getting a technical career is sustaining that technical career over 30 odd years. How would you recommend that students who want to be in the technical field for a long time and contribute over a long period of time, as you have, how do you recommend they approach and sustain their their technical careers?
That is indeed a difficult thing to do. Uh, so as you grow in your technical acumen, you will become more and more specialized. Like it or not, you're going to delve deeper and deeper, whether it's because of work or because of your research. You're going to delve deeper and deeper into very small areas. But as we know, innovation and creativity comes because you get different ideas in the same space. So innovation is nothing but taking ideas that have been implemented successfully in a domain and then applying it to your domain, right? The My thought process with regard to this is always continue to learn, and it's not easy to do that given your constraints of, as you grow, you'll have family, you'll have other commitments that come along, you'll have your own work schedule, and that might be brutal, at least initially, uh, till you kind of make it to a certain level. Or it might continue to be the same because you're enjoying what you're doing, and that's perfectly fine. So, in order to continue to learn, there are standard ways of doing it. Take courses and so on. Uh, Refresh yourself. One thing, for example, uh, in one of the organizations that I worked, we would have to have mandatory 2 weeks of training, and we would go for a particular piece of training, which is public speaking, reading, and writing. And you might say, every year? That's crazy. No, every year you need to renew what you learned and you break some habits that you developed over the year. And I think that's a very good indication from that organization's perspective. It's very important for us to keep learning. And they would fund that. 2 weeks, they'd fund it, you go learn. And yet, of course, you couldn't just learn anything. You learned something that interested you. And if I said I wanted to learn knitting, they would not necessarily stop me from knitting. I would learn knitting for what it was worth. But at the same time, the expectation was that knitting would provide me with some other soft benefit that I could apply back to the company. Now, more importantly, I think much, much more importantly, more than the formal learning and read all these magazines, read Wired all the time, read journals that are important in your domain. The most important piece, I think, is meeting people, meeting people with different ideas. Meeting people with different ideas, even if it's for a cup of coffee, even if you meet them only once every 6 months, meeting people and exchanging ideas, exchanging thoughts. What do you think of? Oh, you're a civil engineer, so you build bridges. Well, I am a mechanical engineer. I build toys, or I build widgets. Now, what's the you start exchanging ideas, and you realize that there may be something that he does or she does that you could use. I'll give you a small anecdote, and this will kind of help frame this. And I think that's the most important part of learning, which is something that over a period of time, because of constraints, because of the way the uh, whole society is structured, it's something that we kind of miss out. We build our own core set of people, and we don't expand every day, every week, every month, which is what we should do, and get more new ideas in. And then when an idea sparks your interest, you need to go deep into it. The anecdote I was going to mention was very simple. And this is, again, how you reach out and then get more ideas, and that'll further your own pathway. The anecdote is very simple. So for 2 years, a couple of professors were troubled by a particular equation. This was in the finance area. And the professors, you'll recognize their names once I kind of mention this algorithm they're working on. They were in the finance area. One was Fisher Black, and the other one was Myron Scholes. And they went to a conference, and they were seated next to an engineer. They did not know. They were chatting, and one of them said, for 2 years, we've been struggling with this darn equation. We don't know what to do with it. The engineer casually looks over and says, that's the heat equation. It's been solved hundreds of years ago. What are you talking about? Heat equation was solved way back when. What? We've been working for 2 years, and we've not been able to solve this equation. Now, I'm not saying that all those three guys, very smart people, but you can be blindsided simply by the narrow focus that will tend to overwhelm you in general. So you have to break out from that. You have to learn. And I will recommend formal learning, whether it's Coursera, edX, or whatever else you want to do. That's perfectly fine. I would encourage, seminars, and you start teaching other people, and that makes your knowledge more strong, if you will. But more importantly, go to random conferences, go to meet new people every week, every month, and you will get new ideas. And then once you get an idea, don't let go of it. Just write it down and probe into it, delve deep into it for about a week or 10 days, see how it kind of shapes your thinking, and then move on. I think that human part of it, where the exchange of ideas is interesting and important, whether it's through Zoom, whether you go for a cup of coffee, or whether it's a seminar that you're attending at out of the blue, it's something that came up. I think that part is key to keeping yourself alive and learning and keeping abreast of what's happening. It can happen even in a business context, but I would urge you to get out of your corporate context and try to expand that to others. Even in your own company that you start working in, your own organization, whether it's university or wherever, go meet the guys who run the facilities department. The facilities, I'm a computer programmer. What do I need? No, I think you'll find it illuminating that they've got a different approach to everything, even problem solving. The way you solve it, they solve it, it might be different. And you say, facilities, why do I need to learn more about that? You don't need to. It is just that will provide you a different perspective. Once again, the stress is that invention is one in a million. Not many people are inventors. It's hard to do. Innovation is being able to apply knowledge that has been tested, implemented, and is successful in one domain to another domain, which is what today lots of people are doing. Whether you look at Amazon, Tesla, Apple, and so on and so forth, that's exactly what they're doing. They're successful not because they're purely inventive. The iPod was the precursor. The iPod was a Sony similar device with the same circular stuff that you use your thumb with and roll. It looks, in fact, if you look both of them, you you'd not know which one is Apple, which one is Sony. But Sony was 10 years ahead of its time. Or the Apple Newton. Apple Newton failed miserably. Apple Newton was 10 years before its time. And so it failed, and so on and so forth. The point I'm trying to make is that it's important to get ideas from other folks and kind of merge that into, and that will help you be on the edge. The last part I'd mention is keep in touch with the younger folks. The younger folks are smarter and they're faster. Every generation is faster than the one before. So work with universities, work with college students, work with high school students, because they're smart and they can tell you what's happening currently in general and where the future is going to be.
Yeah, I think you touched on networking, which was the next question I had. A lot of young students and people trying to get into careers in the technical side often struggle with networking and meeting people within the job market, whether it's at career fairs or whatever it may be. What advice do you have for people trying to navigate the job market and trying to form their own network of people within the market?
Uh, Seriously, the place where you start is your friends and family, right? It's where you have your strongest network. You got the best people who know you, who are going to support you one way or the other. Then you expand that to the folks that you met at the university. Then you expand that to folks that you meet in other contexts, and so on and so forth. But the network is two-way. You get what you give. So it's kind of if you, in most cases, you pat somebody on the back, they'll pat you on the back. So this works effectively in a network, so that you tell them some good things, they tell you good things, and you tell their good things to 100 people, they tell your good things to 100 people, and so on and so forth. That's the key part. Now, how to actually develop and build your network? I think it more often than not, your network will build based on your needs, your wants, and so on and so forth. I did talk about the network being reciprocative. So when you get into trying to network with people, other than people that you know already, especially if you're trying to network with people that you don't know, new professors in some other university, some HR people in an organization, some R&D people in some other organization. There are two parts to this. And once again, I underline reciprocity. One is you have to offer them something that interests them. Number one, that is critical. If you can put in one line, two lines, something that you know that they're interested in, they will respond. It could be anything. It could be that they like skydiving and you like skydiving. You might be interested in R&D. You might be interested in R&D at Facebook about Oculus and so on and so forth. But if you find the guy and you think he's interested in skydiving and you're interested in skydiving, you have to establish that connection. In every meeting, every conversation, you have to remember that you have to give something in order for the other person to come back to you for the next conversation. You don't give, you don't get. And it is true that it's true for the other guy too. He's got to give you something so you'll come back to him for the next conversation. Otherwise, you might not have the conversation. That's the baseline. That's the most important thing that I think when you build a network. Otherwise, it's a network. Otherwise, it's got a network has value only if there's a give and get, and there's a general proactive, if you will, interaction. If there's only a reactive interaction, then it's not really a good network, a good relationship. Most salespeople will send you a LinkedIn invitation, and you may accept all of them, and you might have 500 connections, but maybe only 100 of them are valuable, because the value is what goes on in that connection, what conversations happen, what exchange of information, what values are exchanged, so on and so forth. So that's the most important thing. That's the being able to give something as well as get something. And you might say, I'm a student, I got nothing to give. No, you got something to give. You got something to give in terms of, even in terms of, you find a person who is very interested in the, let's say, artificial limb research. And you say, I'm not really into artificial limb research. Then I say, why do you want to connect with them? But then if you do, or if you are interested, then you have something to give, which is your thoughts. And your thoughts might be naive, simple, ordinary, not at the research level, but that's okay. Because what you've shown is that you're willing to try to contribute something that the other person is interested in. The second piece that I would say that's very important in any relationship, any kind of networking, and you can use all kinds of tools, right? You got LinkedIn, you got all the other, Facebook and this and that. You can link in 100 different ways electronically. The second most important thing that I believe in the in building a network is you have to be active, proactive, passionate about that particular relationship. And if you have got 500 connections on LinkedIn and you speak to the 500 connections once a year, that means you touch each one of them at least once a year, you're doing good. Most people barely touch 50 of them a year, 2 years, or even, in 6 months, they barely touch 100. Now you might say, I put it on my Facebook page and everybody reads it, but that's not the proactive reaching out part, right? That's the, I'm just putting something there and 100 people will see it and maybe someone will comment on it, and that's good. But I think if you want to really strengthen the relationship, it's got to get to more than that. And I think that is how networking has its value. Remember that I talked about the give and get. I talked about how you offer something so that people want to come back for the second conversation. Also, uh, uh, most importantly, if you don't take advantage of your connections for trivial items, which means that you recognize the value of that particular contact, that particular connection, then you'll reap the rewards in spades, because they then realize he did not contact me last 1 year, troubled me for these, but this is really important to him and he's contacting me. That's a great thing. Now I'll turn around and help him, or I'll turn around and work with him, or I'll turn around and see if he can help me. That is very, very important, the value of the connection. Again, numbers matter only as much as you can show that that particular connection has value. And you can actually, you can formalize this in 100 different ways. You can use your supply chain algorithms for this to say, to look at your own, you can graph your own network, Facebook or otherwise, and or all your contacts, LinkedIn, Facebook, Instagram, whatever. You can actually map those and uh, add value to the link between you and them based on simple things. Just do simple thing, number of conversations per year, and you'll realize that some connections are there just because, not because there's tremendous value to that. Then you can harvest the ones that have value. And when you build a new connection, you can go in with the intention of making that connection, that relationship valuable. And I can tell you this right from the get-go. You can make connections with anybody on the face of the earth with today's technology. And if you have something of interest, believe me, they will connect back to you 100%. I've seen this happen over and over and over again. And you might say, I would like to talk to Elon Musk. Either you can reach out to him, and he might, you will find that he might even respond directly back to you one-on-one, if you have something of interest that you might want to think about. Or maybe it's a VC, maybe it's the head of R&D at IBM, maybe it's the head of R&D at Johnson & Johnson, maybe it's the intuitive surgical guy, who lives 3 doors from you, but you can't really go and talk to him. He will respond as long as there is something that connects you to either it's your interest, your passion, or it's his interest or passion, or a combination of both. So don't hesitate, put yourself out there, all social media and elsewhere.
Sounds good. Next question is about a kind of a theory in hardware space. So there was a law a couple of decades ago called Moore's law, where the prediction was that the number of transistors on a microchip would double every 2 years, and the cost of the computers that would have those microchips would be halved. And so essentially, it's sort of graphing out an exponential increase in computing power over the years. And recently, we've observed that this sort of trend has applied almost to computer science jobs and technical jobs as well. That the number of technical jobs, especially in the Silicon Valley, has grown at an exponential rate. Do you think that this trend can be applied to the growth of technical jobs, and do you predict a tapering off in the trend eventually? Nowadays, people are saying that Moore's law, with CPUs getting more and more fast, they're saying that Moore's law might be tapering off. Do you think that can really be applied to the growth of technical jobs in general?
So I'll answer both parts. Moore's law tapering off, it's inevitable that that particular calculation will change. If you said 2 years or 18 months and it becomes 3 years and then it becomes 4 years, it's inevitable. There's the fact that over time that's going to happen. I wouldn't necessarily call that tapering off. I mean, if you look at it from a longitudinal perspective, yes, it looks like tapering off, but in reality, it just shows the increased complexity. Whether you go from, I used to make chips at 100 nanometer scale. Now it's gone to 6 nanometers. Guess what? That took time, but each time I jumped up a manufacturing scale, what happened is I increased the number of transistors I could put on the same area. I increased the power. I increased this. So Moore's law, I would say, from 6 nanometers. Now let's say it takes us another 30 years to get into pure quantum computing. Well, it's kind of the Moore's law, but it's now over a delayed period of time. 6 nanometers, you go to 4 nanometers. 4 nanometers, you go to 2 nanometers. Then you go to molecular size. Then you go to atom size. Then you go to quantum. Is it kind of going to happen? Yes, maybe, but it's going to take a lot longer. Now, as far as jobs are concerned, here's what I think. I think it's not necessarily Moore's law that applies. It's the law of hierarchy. So think about this. Years ago, mainframes, you had some programmers, punch cards, and nobody was allowed into the glass house. So the glass house was where the programmers lived, and they put the punch cards in and so on and so forth. So there were X number of programmers, highly skilled in COBOL, in Fortran, and then Pascal and so on and so forth, but very highly restricted. Let's say there were, for argument's sake, there was one programmer for every 100 ordinary people. Let's just make up a number there. Now, the world has changed. Now, there's no glass house. I mean, there's still glass houses, still mainframes, but the approach to accessing it and working on it's changed. What I hypothesize is that the number of jobs is going to increase, but the people who are going to do those jobs are not necessarily going to be computer scientists or computer engineers. The learning is going to get pushed down further and down further. You're going to have high school graduates who, after finishing high school, will be able to write code and could jump into a programming career straight off. Okay. So what I'm saying is that where you needed really a lot of education, a lot of learning, I think all that's going to be pushed on. As you can see, programming languages, certain of them are very tough. Certain of them are very not tough at all. And there's like no code generators, right? I mean, in the sense that you could write an application without writing a single piece of code. You don't have to write any code. That's coming down. So what happens is you're kind of dumbing down what is needed to write code, to work on, to create an application. You're increasing the possibility of other folks who don't know anything. An accountant. Today, accountants use QuickBooks. Today, engineers use all kinds of tools, and non-engineers use a whole bunch of tools, all of them based on some kind of hardware and some kind of software. As time goes on, over the next generation, it's going to be dumbed down further and further and further and further, that ordinary people. So even though the number of jobs is going to increase, the number of jobs for computer scientists and engineers is kind of going to be potentially at the same growth rate, whereas the potential for all programmers, all technical jobs, all computer related jobs, if you will, is going to expand tremendously. So if I go out and say, if somebody throws a statistic at me and says, oh, we are 150,000 data scientists short in this country, we are 180,000 computer science programmers, computer science students short in this country, I would say, and I would look at history and say, yeah, so what? Because the way technology is going, the way it's building up, there's the top level where it's going to be really complex. You can't do machine learning straight off. You got to learn, you got to have your math proper. You got to know your calculus. You got to know all those basic building blocks are there before you get to machine learning. But the day-to-day programming that happens in business, I'll give you another anecdotal example, if you will, a rough example. CNC machines, those are computer numerically controlled machines, right? Engineers don't write the programs anymore. Those CNC machines are programmed by people on the shop floor who don't have an engineering degree, who don't need a computer science degree. Your process control software, in the olden days, you needed an engineering degree to even look at the box and write code. Process control computers today use English, and you can actually write process control software without having an engineering degree. You might have a degree, you might have a totally different degree. You might be working in an oil refinery, and you may have total knowledge of the oil business, or which pipe goes where and how it gets refined and so on and so forth. You might know nothing about software, but you can write process control software to control the refinery. So it's happening today. It's happening now. It takes a while to get the impact seen, because we are constantly focused on, we need so many data scientists, we need so many computer scientists, because those computer scientists are not necessarily writing CNC code. They used to. 30 years ago, you needed an engineer to write CNC code. They are not the ones who are writing process control software code. They used to. 30 years ago, engineers. You needed an engineer to write the process control software code for the Siemens machines, for the Allen Bradley machines, for the GE machines, GE Fanuc machines, and so on. You needed engineers. You don't need them anymore, because it has been driven down to a level where people, whether using graphical tools or otherwise, can actually write the code to make the machines do what they need to. So in effect, what I'm saying is, yes, the quote unquote Moore's law applicability to the job situation, employment situation in the technical arena is going to continue, but it's the question of the hierarchy and where will you see the most jobs come in over time, and how that's going to happen. So as innovation increases, you'll need more computer science guys. We still have not gotten too far into computer vision. We've still not gotten too far into a whole bunch of things that we need real solid engineers working on. But in terms of the day-to-day and how we push things down to the common man, or the man who does not necessarily know programming, it's that population is huge. That population is huge. That's where the Moore's law effect is going to be seen. uh, Quote unquote Moore's law, you might call it something else for the people part of it. It's going to be very different. another, just an observation is, as machines grow faster, as machines go cheaper, uh, the programming quality generally drops, because if you don't write good programs, you can always increase the memory. You can always get a better CPU. And because of that, what happens is that the the better and better engineers, the guys who write better software and so on and so forth, that tier is going to expand at a particular rate. But the tier which just writes stuff in order to make it work and then increase the CPU or the memory, because they can write bad software. They don't have to write good software at all, because they'll just increase the memory, increase the CPU, and it works, right? They don't, the fact that their loop that they wrote goes through 1,000 iterations when it can do it in 5 is not their problem. I got a machine big enough, so I don't really care. That part, the ordinary programmer who doesn't necessarily understand the basics of computer science or the basic stuff, but can write code that works, that part will grow tremendously.
Yeah. So the final question, which touches on something you mentioned, is what do you see happen in the future in, be it computer science, data science, the technical fields in general? That's the next big thing. So we've had over the last maybe even 60 years, machine learning has come into its own. Now it's been being used a lot more for a variety of applications. We're seeing quantum computing start up and start evolving. Uh, with so much experience in the field, what do you think is the next big leap forward or next big topic of discussion in the Bay Area and the tech community overall?
So, one thing that I've noticed over the last 30 years is the basic concepts remain the same, but because of improvements in other areas, the concepts get applied more efficiently. Whether it is AI, now call it machine learning, and so on and so forth. AI existed, NLP existed for donkey's years, but it's coming to fore now because you can use it. You can actually see it happen because your compute power has gone up. And whether it's, it starts off very simply as neural networks, and they used it for figuring out whether a dam had cracks 30 years ago. And, they used that program for figuring out based on the stress and other data that they collected from the walls of the dam. Well, today you call it machine learning and so on. Parallel programming, distributed computing, existed for years. It existed in hardware, it existed in software, and now you got a whole, cloud-based parallelization concept, and you got Hadoop and this and that, and all that stuff going on over there. My point is that a lot of things get recycled, whether it is something that some mathematician discovered in the late 1800s or early 1900s, and that comes up today, and they say, aha, and then that, now you can, earlier you couldn't compute that, you can compute that, and so on. So I think 80% of what we look at in the computer science industry as what's the next big thing is the next old big thing. It's the old thing which is now facilitated by other things, but it's a self-driving car or even the electric car, electric vehicle. These were experiments conducted, and you can go back in history and look at this, by the big three, and they squelched it. The electric vehicle, they squelched it because they didn't want their monopoly on building these cars to go away. And of course, lots of other things happened. But whether it's, thinking of it from that perspective. However, I think the biggest new revolution is going to be where man meets machine. And I don't mean in terms of man using machine, but the biological interface to a computer. And you look at it from the angle of, let's take several examples, right? You're looking at, let's say, chips. I look at where they are proceeding in terms of not the CPU part, but things like memory. And you figure out that if I can use a cell, a living cell, as a memory unit, that's amazing. I just need to be able to communicate the cell back and forth. You can do that today. But how do I harness it, put it in a manner that's practical and usable and manufacturable and all that stuff is a totally different story. But that's where we are headed towards. We're headed towards that. Whether you look at it from that angle or you look at it from a different angle and say, I want to model. I don't know enough about the human body because we humans, right from the time when Galen came, 1,500 years ago, when started experimenting with cadavers and trying to figure out how the human body worked, and he found all these liquids and he named them and he said there are these 4 liquids and blah 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 and all that. Right from that time to today, we still don't know enough about the human body. We still don't know enough about the human body to figure out how certain things happen. We know a lot. We know a lot about the human body, but if it's on a scale of 1 to 100, we probably know 40. I'd say in certain areas like the brain, we know 10 or 5. In certain things like bones, we've done a lot on bones. We probably know 80%. I think that bringing in technology that mates with biology, not purely data and bioinformatics, but something more deeper. Like I said, could you make a cell a unit of memory? Those kind of things, I think, are the ones that are going to change the way we are working. We talked about quantum computing briefly. If you can get deep into an atom, use it for computing, that's another breakthrough. I think that as we proceed, I don't believe anything of this sort is going to happen in the next 10 years. But I think that we are going to discover things about our human body and and how to kind of mimic it with technology that's going to cause us to do a variety of things. The industry also will kind of come together. I mean, the data science revolution, so to speak, was started 15 years ago by $100 million advertising push by IBM. Nobody was talking about data. Everybody was talking about the big data concept and the fact that McKinsey wrote a paper on that, a 600-page tome on big data, and how over 3 years, IBM had a $100 million campaign to push data 15 years ago. And they pushed and pushed and pushed. And the end result was everybody now focused on data, and they started, data analytics and so on. It helped IBM a lot in selling their stuff. But my point is that industry also will get behind this. I think that that particular piece where, I'll give you a couple of examples and go from there. A blind man who has lost his optic nerve can see because they are able to have cameras fitted which send impulses to the nerve endings on his tongue. The nerve endings on his tongue simulate the optic nerve and send the signals to the brain. Then this person who could never walk on his own can walk without a cane in downtown. I think it's Pittsburgh or somewhere where they did this experiment. And it took them 2 years to do it. I think those are the kinds of things that I think are going to be revolutionary. They sent signals through his tongue, and fooled the brain to think that it's coming from his optic nerve, so that he can see buildings, he can see people, he can walk on the sidewalk, he can recognize the traffic signal, and he can walk. And this is just one example. But I think those are the areas where I think a lot of difference is going to happen in the next 30 years. In the next 10 years, I think we'll still have our standard stuff, right now that what is there, but the slow changes where biology and technology merge. I don't even know what to call it. I can't call it biotechnology, because that seems to be a different kind of term. I can't really think of a term that uh, translates into meaning that I can do stuff with your tongue, which will enable you to see. I can't even think of a term that describes that. But I think those are the kinds of things that are going to make a difference. 30 years from now, maybe half of us will have something hooked to our body, which makes us more, I don't know, perceptive, able to do things which we can't do today, and so on and so forth.
Yeah, that story about the tongue is unbelievable. It's really
It's
unimaginable how that could happen.
interesting. It took them 2 years, and they had to find a volunteer, of course, who would, who would volunteer to do that. They found this, I think it was a 45 or 50-year-old gentleman who'd been blind all his life, and they developed this technology along with him. He was a guinea pig, so to speak, right? So they tested it. Oh, first time didn't work, second time, but he persisted and they persisted, and it took them 2 years, and they perfected it such that he could walk around now. And even those cameras are not even visible. He just wears glasses, zero power glasses, and those are tiny cameras attached to his glasses, so no one knows that he's blind. And he walks, and he can't read a book. Okay, so that let's get that clear. They have not perfected it so that he can read a book, but he can see a movie because they're big and large. He can't read small characters. He's still blind. He's still really physically blind, but he can see big stuff: buildings, cars, people, cats, dogs, fire hydrants. All that he can see, and he can watch a movie. He can enjoy it this time, rather than just hearing stuff, right? So it's fascinating, and there's lots of these things. I mean, there's some work that HP has done in the space. It's what is really sad. I'll say that what I think is really sad is a lot of companies have gone away from doing a lot of this basic research because there's no money in it. You can't really turn around and make it better. There are a few companies which still do it. IBM still does basic research. I don't know of too many companies that do it, but most companies, because they set aside money for R&D, which affects their own game in the future, they don't do much basic research, and basic research is very, very important.
Sounds good. Yeah. Thank you so much for coming on and talking about your experience. It's been really enlightening, to say the least. And thank you so much. I really appreciate that you gave us your time to do this.
You're welcome, and I would definitely like to watch your progress and listen to other interviews that you conduct with other people. I think that it'll definitely be a learning proposition, even for me. I would learn from others that you interview.
Sounds good. Yeah. I look forward to that as well. Thank you so much, and we'll see you later.
Thank you. Take care. Bye.